Page 552, section 8.1. All right, chapter 8 is matrices, and section 8.1 is matrices and systems of equations. When we worked in chapter 7, we looked at lots of different ways that you could solve a system, and we mentioned that in chapter 8 we would solve them with matrices as well. So that's what we want to look at here. To begin with, we need some information about matrices, though. So on page 552 and 553, they give us quite a few bold print terms. They start off with matrix. The plural of that is matrices. And it's basically just a rectangular array of numbers, similar to maybe a spreadsheet, a way of organizing information. In a matrix, you're going to have an order to your matrix, and it is literally just its rows by its columns. Now, I have some people who get rows and columns mixed up. An easy way to remember it is think about like a really nice architectural building downtown that has some columns in front of it. The columns go up and down, right? So your rows are going to go left to right. So you can see we have 3 rows here. And the columns are going to go up and down. So we have 1, 2, 3, 4 columns here. So that would be the order of that matrix. It would be a 3 by 4. Every number in that matrix is called an entry, and each of those entries will have a subscript that will tell us which one they're referring to. The first number will be the row that it's in, and the second number will be the column that it's in. So that would be the entry that's in row 2, column number 3, which would be the 7. A couple more bold print terms. They give us row matrix and column matrix, and they tell me that a row matrix is a matrix that's just made up of a row, one row, and a column matrix is a matrix that's just made up of one column. Right? Now, the way that we're going to use our matrices to help us solve our systems is we're going to take the system and write it in something called an augmented matrix. So here's a system of 3 equations with 3 unknowns, and here is its augmented matrix. And notice that all we do is drop the variables. So I can go through and say I've got 1x minus 4y plus 3z equals 5. So I'm going to keep the 1, negative 4, 3, and 5. 1, negative 4, 3, 5. We put the little dotted line here to separate the coefficients of x, y, and z from the constants. You'll also notice that if I'm missing a term, like that would be 0y, that we fill in a 0 for that. All right? So what would the order for this matrix be, by the way? 3 by 4, right. And that would be the augmented matrix for that system. Now, they also mention in the textbook a coefficient matrix. If I get rid of these constants over here, what I'm left with is just the coefficients. That is a coefficient matrix. And that coefficient matrix is a square matrix. Now, a square matrix is one that has the same number of rows and columns. So it would be like a 2 by 2 or a 3 by 3 or a 4 by 4. Every square matrix is going to have a main diagonal that starts in the first row, first column, and goes diagonally across that square. So that would be a main diagonal. So again, all of those bold print terms on 552 and 553. All right, example number 2, they give me a system of 3 equations with 3 unknowns, and they ask me to write the augmented matrix for it. But I need to be careful because they're going to try and trick me. If you'll notice, this one has an x and a y, but this one has a y and a z, and this one has an x and a z, and they're not even in the right order. So what you might want to do first is go through and rewrite that system with all of the x, y's, and z's filled in and in the correct order, so that then when you come up with the augmented matrix that it's correct as well. So I'm going to put 0 in for z here since that term was missing. I'm going to put 0 in for x in the second row since it was missing. And in the third row, I'm going to need to move the x out to the front, put in a 0 for the y, and then move the z to the back. So I'm going to rewrite that system first before I try and write its augmented matrix. All right, so what's row 1 for my augmented matrix?
1, 3, 0, 9.
Perfect. 1, 3, 0, 9. What's row 2?
0,
And what's row 3?
4, 0, 5.
Yes. So there's my augmented matrix. All right, over on page 554, they tell me that when I'm working with a matrix, there are 3 elementary row operations that I can perform. And because those rows coincide with the equations in the system, we can think of them in that way, that they're operations I could perform on the equations or operations that I could perform on the rows. So the first one says you should be able to interchange 2 rows. Now, come back up here to this system for just a second. Would it make any difference if I switched these 2 equations before I solved? No. If this is equation 2 and this is 3, or this is equation 2 and this is 3, it doesn't make any difference, right? So the same thing should be true over here. I should be able to switch these 2 rows in my matrix without it changing anything. So that is the first thing I'm allowed to do. That's the first elementary row operation, interchange 2 rows. The second one says that I can multiply a row by a non-zero constant. So again, if a row just comes from an equation, if I have this equation right here and I go through and I multiply both sides by 2, as long as what I do to one side I do to the other, that's a legal move, right? So if I'm allowed to do that to the equation, then I'm allowed to do that to the row as well. As long as I multiply that whole row by 2, it's a legal move. That's an elementary row operation that's allowed. The third thing they tell me is that I can add a multiple of a row to another row. That's typically why we did this, right? Like, let's say in this system right here, let's say we were trying to get rid of x. We would multiply this row by 2, and so then I would add negative 2x to positive 2x, and the 2x would eliminate, right? And so we'd be able to get rid of a variable and continue solving. That's why we did that. That is multiplying one row by a constant and then adding it to a second row. So that is, again, an elementary row operation that I'm going to be allowed to do. So let's look at example 3. In example 3C, they give me practice with each of those elementary row operations. So the first one was interchanging 2 rows. I don't think any of us would have a problem with switching row 1 with row 2 or row 2 with row 3. We don't really need to work that out. The second elementary row operation is to multiply a row by a non-zero constant. So let's say I wanted to take row number 1 and multiply it by negative 2. Then literally I'm going to go through and say negative 2 times 1 is negative 2. Negative 2 times 2 is negative 4. Negative 2 times negative 4 is positive 8. Negative 2 times 3 is negative 6. And then the third elementary row operation would be to add a multiple of a row to another row. So right here we've got a multiple of a row, right? That's negative 2 times row 1. Let's add that to a different row. Let's add that to row 3. Okay? So if I want to do negative 2 times row 1 plus row 3, here's negative 2 times row 1. Let's just add row 3 to it. So we could say negative 2 and 2 is 0. Negative 4 and 1 is negative 3. 8 and 5 is 13. Negative 6 and negative 2 is negative 8. So now we've seen an example of all of the elementary row operations. Over on the top of page 556, they define for me row echelon form and reduced row echelon form in a box there on the top of the page, and then they give me a couple of examples of each one. So this comes straight from the top of page 556. I just wanted some examples to be able to point out to you what they were talking about in that box on 556, but these examples are there on 556 as well. All right, it says a matrix will be in row echelon form if it has the following properties. All rows consisting entirely of zeros occur at the bottom of the matrix. So you don't have to have a row of all zeros, but if you do, it has to be at the bottom. So like this matrix over here, the all zero row was at the bottom. It couldn't have been like the second row or the first row and then had other numbers down below it. If it's an all zero row, it has to be at the bottom. Number 2, for each row that does not consist entirely of zeros, the first non-zero entry is 1, and we call that a leading one. So if we look at this one, the first number that's not a 0 is 1. There's my leading 1. The first number that's not a 0 is 1. There's my leading 1. The first number that's not a 0 is 1. There's my leading 1. Same thing here, here, and here. and same thing here and here. So all those ones that are kind of in bold, those are my leading ones. Number 3, if you have two successive non-zero rows, so if you have two rows in order and they're not an all-zero row, the leading one in the higher row has to be further to the left than the leading one in the lower row. So this one is further to the left than this one. This one is further to the left than this one. This one is further to the left than this one, and this one further to the left than this one. You'll notice that they don't have to go perfectly in a diagonal. I didn't have to have a 1 here in order for this to be in row echelon form. It was perfectly fine for the 1 to go all the way over here, as long as the top is further to the left than the bottom. So those are some examples of row echelon form. Then below number 3, it says a matrix in row echelon form can also be in reduced row echelon form if every column that has a leading 1 has zeros in every position and above and below the leading 1. So let's go back to this guy right here. This is in row echelon form. If I also wanted it to be in reduced row echelon form, then every number above and below a leading 1 would have to be a 0. So this 2 would have to be changed to a 0, and that -1 would have to be changed to a 0, so that everything above and below those leading 1s were zeros. Then that would be in reduced row echelon form. So this is in row echelon form and reduced row echelon form. This one is only in row echelon form. So back in section 7.3, your textbook talked about something called Gaussian elimination with back substitution. The problem was, in order to do that, we needed to know elementary row operations, we needed to know matrices, and we needed to know row echelon form. And we hadn't learned any of that yet. So now that we have an understanding of those things, let's look at how we could do Gaussian elimination to solve a system. If we have a system of 3 equations with 3 unknowns and we write it as an augmented matrix like we did earlier in the lesson, to do Gaussian elimination, my goal is going to be to get this augmented matrix to be in row echelon form. Row echelon form is that 1, 0, 1, 0, 0, 1, right? Why would I want to do that? Because back on page 509, we did this exact system, and at that point they told us it was in row echelon form, even though we didn't know exactly what that meant. It was the one that kind of had the little stair-step pattern, and the leading coefficients were 1. The nice thing about that was, when I knew that z was equal to 2, I could just back substitute it right here and say y plus 3 times 2 equals 5. So if y plus 6 is 5, then y is -1. Then once I knew y was -1 and z was +2, I could plug those in and find out that x was +1. So when we had a system that was in row echelon form, all we had to do was back substitute to solve, and it was a whole lot easier to work with. So that's what Gauss suggested. If you have a system with 3 equations and 3 unknowns, instead of combining equations 1 and 2 and creating a new equation 4, and combining equations 2 and 3 and creating a new equation 5, and then taking equations 4 and 5 and solving it as a system of 2 equations with 2 unknowns, I mean, it takes a whole page to do one of those problems, right? What Gauss suggested was, if we don't have to work with all the variables, it's a whole lot faster and easier to just work with the numbers. Let's take that augmented matrix and get it into row echelon form, and then all we would have to do is just back substitute to have our solution. Okay, so how do I get this into row echelon form? When we start on the homework tonight, they're going to, for the first couple of these, they're going to tell me step by step what to do. And then they're just going to say, take the augmented matrix and put it in row echelon form. And we're going to have to figure out on our own what steps to follow. We're going to do one of these each night for several nights, even after we move on from this section, because this is something that just takes some extra practice to really master. Okay, so we start off with comparing our matrix with what we're trying to get to. I need a 1 in the first row, first column. Yep, I got it. They gave me that one as a freebie. I need a 0 right here. Well, I have a -1, so in order to get rid of that -1, I need to add it to 1. In order to get rid of that -1, I need to add it to its opposite, so I need to add it to 1. I have a 1 sitting right here. So I'm going to add row 1 to row 2 so that I can get a 0 right there. That's the logic pattern that we need to develop. Okay? So I'm going to add row 1 to row 2. So 1 and negative 1 is 0. Negative 2 and 3 is 1. 3 and 0 is 3. 9 and negative 4 is 5. All right, so now let's check our progress. I've got 1, 0, 1. Hey, I got another freebie. I was trying to create the 0, and in the meantime, I got a 1. That doesn't always happen, but we'll take it when it does. So I've got 1, 0, 1. Now I need this guy to be a 0. What would I need to put with 2 to get 0? Negative 2. Yes, you are always going to use its opposite. So what if I was trying to get rid of negative 5? What would I need? Positive 5, right. What if I was trying to get rid of 2/3? What would I need? Negative 2/3, right. I always need its opposite. So I need the opposite of positive 2. Do I have one? No. Last time I already had one. I don't have one this time. So if I don't have one, I have to make one. The way that I could make a negative 2 would be to multiply my first row by negative 2, and then I could add it to that third row. So I want to multiply my first row by negative 2, and then I can add it to that third row. Again, that is the logic process that we need to go through. So we'll take negative 2 times row number 1. So negative 2 times 1 is negative 2. Negative 2 times negative 2 is 4. Negative 2 times 3 is negative 6. Negative 2 times 9 is negative 18. Then we're going to add that to row number 3. So row number 3 was the 2, negative 5, 5, 17. So we'll put it right there. Now notice I copy rows 1 and 2 exactly as they are. I don't want to mess up what I've already fixed, right? So I'm only altering row 3 down here. So I can go through then and say, okay, negative 2 and 2 is 0. 4 and negative 5 is negative 1. Negative 6 and 5 is negative 1. And negative 18 and 17 is negative 1. All right, so let's check our progress. We've got 1, 0, 1, 0. I need this guy to be a 0. What's going to make negative 1 a 0? A positive 1, right, the opposite of it. Do I have one or do I have to make one? I already have one. There it's sitting right there. If I did not have one, I could create one, but I already have one. So I can go through and say, let's add row 2 to row 3. I'm going to add row 2 to row 3. Again, I'm not touching rows 1 and 2. I've already fixed them. I don't want to mess them up. So I can say 0 and 0 is 0. 1 and negative 1 is 0. 3 and negative 1 is 2. 5 and negative 1 is 4. And then we can check our progress. So we've got 1, 0, 1, 0, 0. Now I need this to be a 1. This is the first time we've had to create a 1. We've been creating the zeros, but this is the first time we've created a 1. Creating a 1 is really easy because if you multiply any number times its reciprocal, you always get 1. So the way that you can create a 1 is always just multiply it by its reciprocal, right? So if I'm going to multiply 2 by its reciprocal, then that means that I'm going to multiply it by 1/2. So I'll do 1/2 of row number 3. So if I do that, half of 2 is 1 and half of 4 is 2. So now I've got this in row echelon form. And again, Gaussian elimination is take it from its augmented matrix to its row echelon form. Then you can pull the system back out of it and you can back substitute to come up with your solution. And again, that's the same problem we had done before on 509. Now, row echelon form is not unique, meaning we could each sit here and depending on the order that we followed in creating this, we could all come up with a variety of row echelon forms that would all lead to the same XYZ solution would all be right. If I throw this into my calculator and say put it in row echelon form, it's not going to give me this same matrix that I just came up with right here. It's not unique. So Jordan, another mathematician, came along after Gauss and said, hey, if I took an extra couple of minutes And instead of leaving my system in row echelon form, if I would put it into reduced row echelon form, that means that I would have to get these three numbers to be zeros. So I would go on with my same steps for these three numbers, turning them into zeros. When I do that, I am literally staring at my answer. Look, x equals 1, y equals -1, z equals +2. That's reduced row echelon form. That is unique. If I typed the original augmented matrix into my calculator and hit the reduced row echelon form button on my calculator, it will spit that out every single time. That is going to be the fastest, easiest way to solve a system of 3 equations with 3 unknowns, because I will literally be staring at my answer right there. So that's Gauss-Jordan elimination. I don't have to do any of the back substitution. Okay, so I will teach you later how to do this all in the calculator, but for right now we are doing these by hand. So here is our homework for tonight. On pages 562 to 563, we're doing 1, 3, 9, 17, 18, 23, 25, 27, 41, 45, 55. And your challenge is 103. And again, no calculator on these. We will do them with a calculator later on.